Welcome all. Now we'll see the part 2 of chapter 3, which is gears. Gears are defined as toothed wheels which transmit power from one shaft to another by means of successive engagement of teeth. The gear drives offer following advantages compared with chain or belt drives. First thing is, the gear drives are positive drives. It's a positive drive and the velocity ratio remains constant. The center distance between shafts is relatively small and it's useful in compact construction of the device. The center distance between shaft is small, which results in compact construction. Then the gears can transmit large power which is beyond the range of belt or chain drives. So can be used for transmitting large power from one shaft to another shaft, and it can transmit motion at very low velocities. Transmit motion at very low velocity. Then efficiency of gear drive is much higher compared to that of other drives. And it is close to 90% for spur gear. We'll see the details of spur gear. And it's possible to change the velocity ratio over a wide range because of the position of gear shifting. So due to gear shifting, velocity ratios can be changed. So these are the advantages of the gear system over the belt and chain drive. Now we'll see what are the types of gears. Basically, we'll see the classification of gears. Gears are mainly classified into 4 types, which we'll be seeing here. Classified into 4 types. One is spur gear. This is the most common type. Then we have helical gear. Then we have bevel gear. And we have the worm gear. So each gear is used for a particular application. First we'll see about the spur gear. In spur gear, the teeth are cut parallel to the axis of shaft. And the profile of gear tooth is in the shape of involute curve. That is a common in most of the gear systems. We see a involute profile for the gear, and the profile remains the same over the entire width of the gear wheel. So I'll say the profile is involute, remains same over the entire width. And the width of the gear will have the same profile. And this is since the teeth are cut parallel to the axis of shaft, the spur gears are used when we have a power transmission between two shafts which are in parallel. And the spur gears impose radial loads on the shaft. We will see the details about this spur gear. Now this shows a figure. This figure shows the spur gears which are mating. This is a driving shaft and this is a driven shaft. Here you can see this is the shaft axis for both the shaft axes. Both the shafts are parallel to each other, and these are the teeth which are cut on the gear. These teeth are parallel to the axis of the shaft. So that is a specialty about the spur gear, and these are used for transmitting power when we have the situation arises such that we have to transmit power between two parallel shafts. Then spur gears are used. Now we will see the second type of gear, which is a helical gear. The second type of gear is the helical gear, and a pair of helical gears is shown in this figure. The teeth of this gear are cut at an angle to the axis of the shaft. We can know that this is the axis of the shaft, and the teeth are cut at an angle to the axis of the shaft. But here also the profile of the gear will be involute, and the profile will be involute in any plane which is perpendicular to the tooth. Like if you cut any plane which is perpendicular to the tooth, the profile of the gear will be a involute profile. Now we will go to the third gear, which is nothing but the bevel gear. So this figure shows the pair of bevel gears. The bevel gears have a shape of a truncated cone. This, if you extend, you can know it will be a cone. So it will be a shape of a truncated cone, and the size of the gear tooth decreases towards the apex of the cone. Bevel gears are normally used for shafts which are at right angle to each other. So that is an important point. So used for shafts which are at right angle. So bevel gears are mainly used when we have to transmit power between two shafts which are perpendicular to each other or which are at right angle to each other. And it's not a very rigid condition. The angle can be slightly more or less 90 degree, more or less than 90 degree. Now in this bevel gear also we can have a straight cut as well as a spiral cut, and this bevel gears impose radial loads and thrust load on the shaft. Radial loads and thrust load on the shaft. So that is about the bevel gear. Then we will see the fourth type. It's nothing but the worm gear. So what is worm gear? This figure shows a worm gear which consists of a worm and a worm wheel. This is the worm wheel, and this is the worm. The worm is a form of a threaded screw which meshes with the matching wheel. The threads on the worm can be single or multi-start and usually have a small lead. Worm gear drives are used for shafts where the axes do not intersect and are perpendicular to each other. Now here this is a different application. Here you can see that axes are not intersecting, are non-intersecting, and they are perpendicular to each other. That is a specialty of the worm gear. It is used when the two axes are perpendicular to each other. This is coming out of the board, and this will be this way. So they are perpendicular to each other and they are non-intersecting also. And in such cases we use the worm gears, and worm gear impose high thrust load. Thrust loads, and they are mainly used for in application where we need a high speed reduction. These are mainly used when we need a high speed reduction ratio, and generally the speed reduction ratio offered by the worm gear will be like 60:1 to 100:1. This kind of a reduction in velocity ratio can be achieved by using a worm gear. And so that is a basic classification of these gears. So we have seen the spur gear, helical gear, bevel gear and worm gear. Spur gear and helical gear are used when the shafts are parallel, while the shafts intersect at right angle, then bevel gears are used, which is shown here. When the shaft intersect at right angle and the axis of the shaft will be intersecting and they will be at right angle to each other. And worm gears are recommended when the axis of shaft are perpendicular and non-intersecting. And when the axis of shafts are neither perpendicular nor intersecting, then spiral helical gears are employed. And the speed reduction ratio for the helical gears and spur gears are generally in the ratio of 6:1 to 10:1. And in the case of bevel gears, it is almost in the ratio of 1:1. The speed ratio for the normal velocity ratio for a pair of bevel gears 1:1, and which can be increased up to 3:1. And for high speed reduction, we have seen that worm gears have to be used, and the velocity reduction ratio obtained in worm gears is of the order of 60:1 to 100:1. So depending upon the application, so we can choose the type of gears. Now we will see what are the basic terminology we use in gears. So this is the figure showing a gear. One of the tooth of the gear is shown, and this is along the width. So these circles lie in the plane, in this plane. The circles which I have drawn here, this will be lying in this plane, and this is out of plane. So terminology of this spur gear is shown in this figure. First we have a pitch circle. So pitch circle is a circle which is shown here. It's a theoretical circle upon which all calculations are usually based, and the diameter of the pitch circle is called the pitch diameter. Shown as D. Pitch diameter is the diameter of the pitch circle. When two gears are mating, usually the smaller of the gear is called a pinion. The smaller of the gear is called a pinion, and the larger one is called a gear. This is for when a mating takes place. Now we have another term, circular pitch. Circular pitch, denoted by small p, is a distance measured on the pitch circle. This is the distance measured on the pitch circle from a point on one tooth to the corresponding point on the adjacent tooth. So if I have another tooth here, like this, the distance from this point to this point along this pitch circle is called the circular pitch. So what can we say if n is the number of teeth? If n is the number of teeth in the gear, we can say circular pitch will be pi d, that is the circumference of the pitch circle, divided by n. This will be the circular pitch. And circular pitch is equal to the sum of tooth thickness plus width of space. tooth thickness plus width of space. This much portion is called the tooth thickness and this much portion is called the width of space. So that will the sum of these two will give the circular pitch. Then we have the fourth one, which is the important one, which is module, denoted by letter small m. Module is a ratio of the pitch diameter to the number of teeth. So module is given by pitch diameter to the number of teeth. Then we have another term called diametral pitch. Diametral pitch denoted by capital letter is the ratio of number of teeth on the gear to the pitch diameter, or this can be said as inverse of the module will be the diametral pitch, denoted by capital P. So that is about the diametral pitch. Then we have another parameter called the addendum of the circle and dedendum. The addendum of the circle is the radial distance between the top land. This is called the top land. It's a radial distance between the top land and the pitch circle. Pitch circle is called this top portion is called the addendum. And similarly, the dedendum is a radial distance from the bottom land to the pitch circle. And the full depth is the sum of the addendum and dedendum. So addendum denoted as letter A is a radial distance between top land and the pitch circle. And dedendum denoted by letter B is the radial distance between the bottom land and the pitch circle. And the pitch circle. So from the diametral pitch and the circular pitch, diametral pitch and circular pitch, we can say that diametral pitch into circular pitch will be given as pi. Diametral pitch is n by d, circular pitch is pi d by n. So diametral pitch into circular pitch will give it as pi. So these are the basic terminologies we come across in gear, which will be useful in the further explanation of the gear. Now, if two gears are mating, whose pitch circle diameters are dA and dB, now the central distance between the two gears, central distance will be given as half of dA plus dB, that will be given as half of m by 2 into NA plus NB. It's the central distance. When two gears are mating, the distance between the two centers are given by half of dA plus dB, that is half of diameter of first shaft to diameter of second shaft. That will be equal to m by 2 into Na plus Nb, where Na is the number of teeth in the first shaft, Nb is the number of teeth in the second shaft or B shaft, and m is the module. So with this information about the module and number of teeth, we can find what is the distance between the two shafts which are mating with each other. Now we will see the next portion, which is nothing but law of gearing. Which states that the common normal to the tooth profile at the point of contact should always pass through a fixed point called the pitch point in order to obtain a constant velocity ratio. That is, common normal to the tooth profile at the point of contact should always pass through a fixed point. To a fixed point called the pitch point. In order to have a constant velocity ratio. That is, if we have two gears which are mating with each other, and this is the point of contact, then this point of contact should always pass through a point P, which is the pitch point. And in such cases, this line will be, that is what we say is, this line should be passing through a point which will be the pitch point P. This point is called the pitch point P, and this line is called the pressure line. The line through which the contact takes place is called the pressure line, and the angle made by the pressure line with the horizontal is called the pressure angle. Alpha here will be called the pressure angle. So whenever two gears are mating, the tangential velocity of one should be equal to the tangential velocity of 2, or we can say r1 omega 1 is equal to r2 omega 2, or we can say d1 omega 1 is equal to d2 omega 2, or we get a relation for law of gearing. We get the relation as omega 1 by omega 2 is equal to d2 by d1, where d2 and d1 are the pitch circle diameters, and omega 1 and omega 2 are the angular velocity of both the shafts or both the gears. Of gears 1 and 2. And for the constant velocity ratio, we can also find a relation that d1 plus d2 should be a constant. And what is d1 plus d2? That we have already seen that is equal to m into n1 plus n2 should be a constant. And for the constant velocity ratio, omega 1 by omega 2 should be equal to d2 by d1, and the point about which the point at which the contact take place should be passing the normal to the tooth profile at the point of contact. At the point of contact, the normal will be like this, and this normal to the point of contact, normal to the tooth profile at this point of contact should always pass through a fixed point called the pitch point. In that case, we can get a constant velocity ratio, and omega 1 by omega 2 will be given by d2 by d1. And it has been found out that only involute and cycloidal profile, and cycloidal profile satisfy the fundamental law of gearing. Law of gearing. And out of these two type of profiles, involute and cycloidal profiles, the involute profiles are most commonly used in gears, because for involute profiles the pressure angle, that is the angle which the pressure lines makes with the horizontal, remains same, whereas in case of cycloidal curves, the inclination of the pressure line with respect to the horizontal, that is a pressure angle, keeps on varying. That is for cycloidal curves. For cycloidal profile, alpha varies, therefore not used commonly. Now we will see the force analysis on gears. In gears, the power is transmitted by means of a force exerted by the tooth of a driving gear, that is this gear, on the meshing tooth of the driven gear. And according to the fundamental law of gearing, we have seen that the normal force always acts along the pressure line, and alpha will be the pressure angle. This is shown here. The normal force will be always acting along the pressure line, and the pressure line makes an angle alpha with the horizontal, where alpha is called the pressure angle. So this normal force exerted on this driven gear tooth will have two components. One is a radial component and one will be the tangential component. We will see that. So this is the Pn. Pn is the Pn is a normal force exerted by driving gear tooth on driven gear tooth. And this normal force makes an angle of alpha, which is nothing but the pressure angle with the horizontal. Therefore, this normal force will have two components, the tangential force and the radial force. The tangential force component, so if the tangential force component is known, we can say the normal force component will be Pt by cos alpha, and Pr is equal to Pt tan alpha. So once we know the tangential component, we can find out what is the normal component and what is the radial component. So how do we know the tangential component? Usually the gears are used for transmitting the torque from one shaft to another shaft. So if we know what is the power transmitted by the shafts, and if we know the RPM of the shaft, then we have the general formula 2 pi nt by 60 is given by P, where P is the power transmitted T is the torque transmitted and N is the RPM of the machine. So if this is known, we can find what is the torque transmitted, and in the case of gears, what will be the torque transmitted? Torque transmitted T will be equal to PT, that is a tangential force, into the diameter pitch diameter by 2. So torque will be PT into D by 2. This will be the torque transmitted. So from the power transmitted, we can find what is the torque transmitted, and from the torque transmitted, knowing the pitch circle diameter, we can find out what is the tangential component of the force. And once we know the tangential component of the force, and if we know the pressure angle, then we can find what is the normal force and what is the radial component of the force. And this tangential component of force is useful in transmitting the torque from one shaft to another shaft, and the radial component only acts on the shaft bearings. So this is the basic analysis of the gear tooth, and in this analysis we have made some following assumptions. As the point of contact moves, the magnitude of the resultant force Pn actually changes, but this effect is neglected. And another basic assumption is that we are assuming that during mating only one pair of teeth takes the entire load. That is a major assumption which we take here. That is, only one teeth is in contact with each other. In reality, at times there are two pairs which are simultaneously in contact and they share the load. And this aspect is not considered in this analysis. For this analysis, we consider that only one pair of mating tooth, one pair of teeth in contact. And this analysis is valid under static condition, that is when the gears are running at low velocities. So these are the basic assumptions in the force analysis. These basic assumptions we are using for making the analysis simplified, otherwise it gets complicated. Now we will try to solve a simple problem to illustrate the concepts of force analysis and laws of gearing. A 20-degree full depth involute spur pinion of 4 mm module and 21 teeth is to transmit 15 kilowatt power at 960 rpm. Its face width is 25 mm. What will be the tangential force transmitted in newtons? So as I have been telling, first we listed what are the parameters given. Then the module is given as 4 mm and number of teeth is given as 21. Power transmitted is 15 kilowatts, so 15,000 watts, and the RPM is 960 RPM, and the face width is given as 25 millimeter. Now the power is given and RPM is given. So what will be the torque transmitted? Torque transmitted can be found out by the relation P is equal to 2 pi n T by 60. Therefore torque T will be 60 P divided by 2 pi n. Here it will be 60 into what is power? Power is 15,000 watts divided by 2 pi into n is the speed in RPM, that is revolutions per minute. So what will this give? This will give 60 into 15,000 divided by 2 pi into 960. That will be 149.2 Newton meter. So how do you find the force transmitted? We know that torque transmitted T is equal to the tangential component of force into D by 2, where D is the pitch circle diameter. Now how do you find the pitch circle diameter? What other information we have? We have the module and we have number of teeth. What is module? The module is defined as the ratio of pitch circle diameter to number of teeth. So from this we get D is equal to M into N, that's equal to 4 into 21 is equal to 84 mm. So we get torque is equal to PT into D by 2, or we get PT is equal to 2 torque divided by D, that's equal to 2 into 149.2 Newton meter divided by D is 84 mm. So 84 into 10 power minus 3. So this will be 2 into 149.2 divided by 84 into 10 to the minus 3. This will be 3552 newtons. So you can see this question is quite simple, and this was asked in the GATE 2009. So if you know the concepts clear, there's no scope of any confusion here. You can easily find out what will be the force transmitted or tangential force transmitted by using the simple relations. Now we will see another problem. A gear set has a pinion with 20 teeth and a gear with 40 teeth. The pinion runs at 30 revolutions per second and transmits a power of 20 kilowatts. The teeth are on a 20-degree full depth inverted system and have a module of 5 mm. The length of line of action is 19 mm. Find the center distance for the above gear set and resultant force on the contacting gear tooth. So we can list out what are the parameters given. So for pinion teeth, they are given number of teeth. N1 is equal to 20. And for the gear, it is N2 is equal to 40. The pinion runs at the RPM is given as 30 revolutions per second. Or this will be equal to 30 into 60, that is 1800 RPM, and transmits a power of 20 kilowatts, 20,000 watt. And the pressure angle will be 20 degree because it's a 20 degree full depth system, and the module of the gear system is given as 5 mm. Now what is the center distance for the above gear set? So what is the center distance? We know center distance is given as 1 by 2 into D1 plus D2, where D1 and D2 are the pitch circle diameter for the two gears, or this can be written as M by 2 into N1 plus N2. So in this case it will be M by 2 will be M by 2 millimeters, so into 10 raised to minus 3 into 20 plus 40 be how much? 20 plus 40 is 60, 60 by 2 is 30, 30 into 5 is 150 into 10 power minus 3 meters. That is 150 millimeters will be the center to center distance. Center to center distance for this gear set is 150 millimeter. So this is the first part of this question. Now second part, they have asked what is the resultant force on the contacting gear. So for that we have the power transmitted is given as 20,000 watts, and the RPM is given as 1800 RPM. So what will be the torque transmitted? You know the torque transmitted will be 60 P by 2 pi N. So that will be 60 into 20,000 divided by 2 pi into 1800. Be how much? Be given as 106.1 Newton meter. This is the torque transmitted. So what will be the force transmitted? We know torque transmitted is equal to force transmitted into D by 2. So here D will be how much? 20. It will be 20 into 5 because the force is transmitted by the pinion. So here PT will be given as 2T by D equal to 2 into 106.1 divided by D is the diameter for the pinion. Diameter for pinion will be N1 into M, that is 20 into 5. So it will be 100 millimeters. So this will be 2 into 106.1 divided by 100 into 10 to minus 3. That will be 2122 newtons. This will be the tangential force transmitted. So what will be the resultant force? Resultant force on this contacting system will be, we know that resulting force P will be equal to Pt by cos alpha. So that will be 2122 divided by cos of 20. That will be 2122 divided by cos 20. This will be 2258. So this will be the resultant force acting on the gear. So thus we can, with the basic force analysis and laws of gearing, we can solve this problem. This is also a gate question. It was asked in gate 2007. So these kind of questions can be easily answered once you know the concepts clearly. Now we will see the important concept of beam strength of a gear tooth, or Lewis bending equation, or Lewis bending equation. The analysis of bending stresses in a gear tooth was done by Mr. Wilfred Lewis in the paper Investigation of Strength of Gear Tooth. Even today, the Lewis equation is considered as a basic equation in the design of gears. In Lewis analysis, the gear tooth is treated as a cantilever beam as shown here. The tangential component of force, which we have found out earlier, causes the bending moment about the base of the tooth. And Lewis equation is based on the assumption that effect of radial component is neglected. So to start with, I'll see the basic assumptions are: the basic assumption in Lewis equations are the radial forces are neglected, the effect of radial forces are neglected, and it is assumed that the tangential force is uniformly distributed along the width of the gear. Then stress concentration is not considered. And it is assumed that only one pair of teeth in contact. So these are the basic assumptions in the formation of a Lewis equation. Now we have seen that what will be the bending, the tangential forces will be causing the bending of this tooth about the base. So the bending moment which causes this failure will be given as Pt into h, which will be the bending moment about this axis, about the root of the gear. And what will be the moment of inertia? Moment of inertia will be, if this will be a cross section, will be rectangle of width b and thickness t. So the moment of inertia will be bt cube by 12, and therefore the bending stress sigma will be given as my by I. And what is y? Y is, in this case, y will be half of this height because it is bending about this axis. Now the neutral axis, if you draw, it will be like this, centroidal axis. So when it bends, so when it is bending, the half of this height will be t by 2. So y will be t by 2 here. So what will be the bending stress? Bending stress will be Pt into h into t by 2 by bt cube by 12. That will be 6 times pth by bt square. The bending stress will be given as 6 times pth by bt square. So from this we can say the tangential force Pt should be sigma times bt square divided by 6h. So now I multiply the numerator and denominator by the module m. Then I take the factor t square by 6hm outside. So I'll be getting mb into sigma into t square by 6mh, and this can be written as mb sigma into capital Y. The capital Y is equal to t square by 6hm. This is called the Lewis form factor. So your bending, the tangential force will be m into b. M is the module, b is the width of the tooth, sigma is the bending stress, y is the Lewis form factor. So when the tangential force is increased, the stress also increases, and when the stress reaches the permissible magnitude of bending stress, then the corresponding value of Pt is called the beam strength. When sigma becomes the permissible value, Pt is called the beam strength, denoted by letter SB. So we can write SB equals mb sigma y. I'll write as sigma b. Where sigma b is a permissible bending stress, m is a module, b is the width of the gear tooth, and y is a Lewis form factor. Therefore we can write the beam strength is given as m b sigma b into y, where SB is a beam strength, m is a module, b is a width of the gear tooth, sigma b is a permissible bending stress, and y is the Lewis form factor. And in order to avoid the breakage of gear tooth due to bending, the beam strength SB should be greater than or equal to P effective. And usually we in design of gear tooth, sigma b is taken as SUT by 3, where SUT is the ultimate tensile strength of the material. Therefore, in design of gears, it is required to decide the weaker part between the pinion and the gear. So from this equation, SB is equal to MB into sigma b into y. M into B will be remaining same for pinion as well as gear. M into B term will be same for pinion and gear. So the only term which decides the strength will be sigma b into y. So which one has a higher value of sigma b into y? That will be the stronger part. The other one will be the weaker part. Generally, when different materials are used, the product of sigma b into y decides the weaker portion between pinion and gear. Usually it is seen that Lewis form factor y for pinion is always less, is generally less than that for gear. And when the same material is used for pinion and gear, the pinion is always weaker than the gear. Therefore, when in such cases, since the y pinion is less than y gear, therefore we should choose a different material for pinion such that sigma b for pinion should be greater than sigma b for gear, or the ratio of the product of sigma b into y should be same for both pinion as well as gear. So now what is P effective? This is the effective load on the gear. Effective load on the gear can be defined as, if P effective is PF is the effective load, the effective load can be denoted as CS into PT divided by CV, where CS is called the service factor and CV is called the velocity factor. And why we use a service factor is because generally when we have a power transmission from one shaft to another shaft, the torque developed by the source of power varies during the work cycle. Therefore, the torque required by the driven machine also varies, and this is balanced by means of a flywheel. But in gear design, the maximum force is the criteria. So this is accounted by means of the service factor CS, which is given as a ratio of maximum torque to the rated torque. It's called the service factor, that is maximum torque divided by the rated torque. So that is about the service factor. And in addition to the static load due to power transmission, there is a dynamic load between the meshing teeth. The dynamic forces, that is dynamic effects, are included by means of this velocity factor. And what are these dynamic factors? This dynamic factors is induced due to inaccuracies in the tooth profile, or it can be due to the errors in tooth spacing, or it can be due to elasticity of the parts, or it can be due to inertia of the rotating masses. Therefore, in order to account for these dynamic effects, the velocity ratio CV is considered, and we get P effective as CS by CV into PT. Now, how do we do the design of the gears based on these parameters? Now, for the design of gears, we have seen earlier that the beam strength should be greater than or equal to P effective. What is the beam strength? Beam strength is given as MB into sigma B into Y, where Y is given as, Y is the Lewis form factor, which is given by T square by 6 HM. And what is P effective? P effective is given by CS by CV into PT. And what is PT? If P is the power transmitted, and N is the RPM, then we have the torque transmitted will be 60 P by 2 pi N, and the P tangential will be torque by D by 2, that will be equal to 60 P by pi N D. And what is D? D can be written as M into N, where M is a module, N is the number of teeth. So we can write P effective is equal to CS by CV into PT, that's equal to CS by CV into 60 P by pi N M capital N. Well, P here will be the power transmitted. Don't get confused with the nomenclature. In this equation, P is power transmitted, N is RPM of the machine, M is the module, and N is the number of teeth. And CS and CV are the service factor and velocity factors. And SB is given us, so we have SB should be greater than or equal to P effective. So in the worst case we can say that SB should be equal to P effective into some factor of safety. So we can say SB is equal to, we know that is equal to sigma B into Y should be equal to P effective into some FOS, factor of safety. And what is P effective? That we have already found out. CS by CV into 60 P by pi N M capital N into factor of safety should be equal to MB sigma B Y. So from this relation we can find out what will be the module of the gear tooth. We can find out what should be the module for this mating gear system. Here in this equation I will write out what are the parameters. B is the width of the gear, sigma B is the bending stress, or I can say that the sigma B should be the permissible bending stress, Y is a Lewis form factor, P is the power transmitted, N is the RPM of the machine, M is the module, capital N is the number of teeth, and FOS is the factor of safety. And CS and CV are the service factor and velocity factor respectively. So with this we can find out what should be the module for the design based on beam strength. Now we will try to solve another problem. This problem we have seen earlier also. A 20-degree full depth involute spur pinion of 4 mm module and 21 teeth is used to transmit 15 kilowatt power at 960 rpm. Its face width is 25 mm. The tangential force transmitted is that we have calculated earlier. There is a small addition to this question. So given the tooth geometry factor is 0.32 and the combined effect of dynamic load and allied factors intensifying the stress is 1.5, what will be the minimum allowable stress for the gear material? Now we have the basic equation MB sigma By is equal to CS by CV into 60P by pi N into factor of safety. Now as we do in other problems also, we will try to list down what are the parameters used here. Okay, here what are the parameters given? It's given as modulus 4 mm, that is 4 into 10 power minus 3 meters, and number of teeth is 21, power transmitted is 15,000 watts, The RPM given by small n is 960. Face width B is 25 into 10 power minus 3 meters. And the tooth geometry factor Y is 0.32. Combined effect of dynamic loads and allied factors intensifying the stress is 1.5. That is, the factor of safety is 1.5. Then what is the minimum allowable stress for the gear material? Now substituting the relations, what we get? M, in this relation, M is a module which is given as 4 mm. B is a face width given as 25 mm. Sigma B is what we have to find out. And the form factor Y is 0.32. Then CS and CV, if it is not given, we can take it as 1. P is the power transmitted given as 15,000 watts. Factor of safety is given as 1.5. Pi. N is the RPM of the machine is given as 960. M is a module, again 4 mm. And N is number of teeth 21. So it is just a substitution. So what do we get is 4 into 10 power minus 3 into B. B is 25 into 10 power minus 3 into sigma B into 0.32 is equal to 1 by 1 into 60 into P is 15,000 divided by pi into N is the RPM is 960 into M is the module is 4 into 10 power minus 3 into capital N is the number of teeth 21 into factor of safety is 1.5. So what will be sigma B? It's just substitution of the values. So it will be 60 into 15,000 into 1.5 divided by pi into 960 into 4 into 10 power minus 3 into 21 into 4 into 10 power minus 3 into 25 into 10 minus 3 into 0.32. This will be equal to 166.5 MPa. So this way we can easily find out what will be the stress in the stress coming in the gear material given the type of loading acting on it as well as the tooth geometry. Once these two parameters are given, we can find out what will be the value of the stress coming in the gear tooth. So that is about the Lewis equation and the bending strength of gears. So we'll see another small problem. A 20-degree full depth involute profiled 19 tooth pinion and 37 tooth gear are in mesh. If the module is 5 mm, what is the center distance between the gear pair? So this we have solved a similar problem earlier also. Here we list down what are the parameters given. N1, that is number of teeth in the pinion is 19. N2, number of teeth in the gear is 37. The module of the gear is given as 5 mm. Therefore, what will be the center distance? Center distance will be d by 2 into, 1 by 2 into d1 plus d2. In terms of module, it will be m by 2 into n1 plus n2. So here it will be 5 by 2 into 19 plus 37. So 2.5 into 19 plus 37, that will be 140 mm. This will be the center distance between the two shafts. This was asked in GATE 2006. So it's all simple substitution of formula only, and if you know the concepts very clearly, then you can easily solve these kind of problems. We have another problem here. Two mating spur gears have 40 and 120 teeth respectively. The pinion rotates at 1200 rpm and transmits torque of 20 Newton meter. The torque transmitted by the gear is. Now we will list down the parameters as usual. So N1 is the number of teeth in the pinion is given as 40. N2 is the number of teeth in the gear is 120. The pinion rotates at at a speed of n is equal to 1200 rpm and transmits a torque equal to 20 Newton meter. Then what will be the torque transmitted by the gear? Now the torque transmitted is given as Pt into d by 2, or we can say it is given by Pt into d is nothing but m into n by 2. We list out the equation in terms of the variables available. So here n and m are available. So T is equal to Pt into nm by 2. So when we have a mating of two gears, the force exerted by one gear on the other will be same as the by action reaction principle. Pt should be same in both the cases, or we can say Pt is nothing but 2T by mn is equal to Pt. So Pt1 is equal to 2T1 by m1 n1 should be equal to 2T2 by m2 n2. So here when we substitute, we get, or we can say T1 by n1 is equal to T2 by n2, because m1 is equal to m2. So from this what we get, T1 is given as 20 Newton meter, 20 divided by n1 is 40 is equal to T2 divided by n2 is given as 120. If we get T2 is equal to 20 into 120 divided by 40, this is nothing but 60 Newton meter. Therefore the torque transmitted by the gear will be 60 Newton meter. Thus these are all problems which can be solved by basic concepts. So once a concept is clear, this kind of problems can be easily solved. So with this we come to the end of part 2 of this chapter 4 on gears.